Welcome back. In the last video, we prepared our data to be used with a pre-trained ViT feature extraction model. And I issued you the challenge of training it. How did it go? I hope you tried it out. If not, let's now do it together. Let's see if we can outperform our custom built model. Import engine, and we're going to create an optimizer. Create optimizer, and we'll create a loss function while we're here. In line with the paper and in line with what we've done before, we're going to stick with the torch.optim.atom optimizer. Lots of typos here. We'll optimize the parameters of our pre-trained ViT. .parameters. Of course, there will only be the trainable parameters in the head layer, so the classification layer. We'll set the LR to 1E-3, and we'll create the loss function, which is going to be torch NN cross entropy loss for multi-class classification. And now we have trained the classifier head of pre-trained ViT. Let's adapt this pre-trained ViT to our own food vision mini problem. Let's set the seeds. We'll go pre-trained ViT results equals engine. So we're importing our engine function or our engine script, and then we can leverage the train function here. Model is going to be our pre-trained ViT. Then we'll use the train data loader parameter and pass in train data loader pre-trained, because this training data loader has been formatted with a transform that is associated with our pre-trained ViT. We got that from here. And then we can do the same with the test data loader to make sure our data has been formatted in the same way that our pre-trained model has been trained on. Then we want to pass in the optimizer. Loss function equals loss function. Epochs, we'll use 10 as well, just as we did above. And then we'll set the device to the device, which is of course CUDA. Now, are you ready? We're going to train a pre-trained ViT model, or just the feature extractor version, on our food vision mini data. Do you think it'll beat our own custom ViT? Let's find out in 3, 2, 1, model training. Okay, good. No errors so far. This should be quite quick because our model is pre-trained and it's only updating a certain number of parameters in the head layer. Oh my gosh, we're at 90% accuracy already. And 95% accuracy on the training data set, 97. The loss is going down. That's exactly what we're after, 92.8. Oh, we drop down to under 90. Or lower again. Oh, back up near 94. And we finish, oh my gosh. The loss has gone in the right direction on that. Well, okay, so it looks like a pre-trained model has performed far better so far than our own custom implementation and quicker. So 3.3 seconds per iteration. And we have, what did we get before? 5.45 seconds per iteration. And we finished with an accuracy of 26%. Oh my goodness. Well, let's plot some loss curves and get visual. Let's see what's going on. I think this might be our best performing model yet. So I think we're up to 10.5. Plot the loss curves of our pre-trained ViT feature extractor model. So we've got pre-trained ViT results. I'll just copy this in here. And so we can go from helper functions, import plot loss curves, and then we'll get visual. I have a feeling these are going to be some good looking loss curves. You ready? Oh my goodness. Don't they look good? So the loss is going in the direction we want and the accuracy is going in the direction we want as well. So if we go back to here, are they some good looking loss curves? So they're not exactly in the Goldilocks zone, but they certainly look much better than what the ones we got before. So I'll let you have a think about how we might even improve these even further. The number one thing would probably be what we've discussed before, and that is, we go back up here, this one, more data, because that's generally the best way to improve a deep learning model. But for now, those are some pretty darn good results. And I hope you're also now seeing the power of transfer learning, is that we spent a fair bit of time replicating a vision transformer architecture from scratch, but within one section, and in fact, probably, I would say maybe 20 lines of code total. We're a little bit verbose, so maybe you could do less. With 20 lines of code and the power of torch vision.models, the pre-trained models and pre-trained weights, we got some outstanding results using transfer learning on a small amount of data. And in fact, there's some other weights here that you could try that get even better results on ImageNet. In fact, I'm going to set that as an exercise for this, is to try out the swag weights. And you can read how the swag weights were obtained there, but it's going to be a very similar process to what we've just done. But if you go back to PyTorch transfer learning, there are several other places to find pre-trained models for your problem. And you can get great results, as we've just seen, with small amounts of data. So the PyTorch domain libraries, Torch Vision is what we just used. Hugging Face Hub is another great place. There's datasets there as well. The TIM library for PyTorch image models. So if we click on that, that's available on GitHub. That's got a lot of pre-trained vision models there. And then, of course, there's Papers with Code, which is state-of-the-art machine learning research with code implementations attached. So with that being said, I think there's one more thing for us left to do. Or actually, maybe two. Yeah. So since we've got a pretty good performing model here, we've seen the loss curves, how about we save it? So 10.6, is that what we're up to? 10.6. We'll save our best performing ViT model. So that's my challenge to you. Save the best performing ViT model, which will be the pre-trained ViT model, performed better than our custom built one trained from scratch. And then we're going to inspect how big the model actually is. Because although this model may be the best performing we've got, its file size may be too big for us to deploy it. And we'll see what I mean by that later on. I'll see you in the next video.